So we're talking next about chapter 17, acid base. Were there any questions on chapter 16, diluted solutions?
That's crazy. So it's pretty much just straight calculation.
The chapter 16? Pretty much just some vocabulary, saturated, supersaturated, solubility, that kind of stuff, and calculations. Solute, solvent, titration. So take a look at the calculations there. We'll come back to it, the questions about the calculations. But for now, we're going to skip over this chapter 17, acid base. There are three definitions for an acid base. Arrhenius. Arrhenius acids have H+. Arrhenius. Arrhenius base is hydroxide, OH minus. So Arrhenius acids have H+, Arrhenius bases have hydroxide. But not everything fits. For example, ammonia. Does ammonia have a hydroxide? No, it's NH3. Is ammonia a base? Yes, it's a base. But it doesn't have hydroxide. It can make hydroxide, but it doesn't have hydroxide. And so it wouldn't fit this definition. So Arrhenius is very narrow. It's too narrow of a definition. The Arrhenius acid-base reaction, there's only one. Do you know what the Arrhenius acid-base reaction is? It's H plus OH minus. H plus OH minus makes water. And that's it. And so Arrhenius we're not going to do anything with. Bronsted we are. So Bronsted is more powerful. So Bronsted looks at it from the perspective of an H plus remover and an H plus source. So the base is the H plus remover. It takes H plus. This base, does it have any hydroxide? It's ammonia. No, but it can take an H plus. This acid, is it H plus? Not really. It's H2O. So it doesn't really fit Arrhenius, but it fits Bronsted. So again, just simply, acid is an H plus source, base is an H plus remover. So bases attack acids, this is what we say. So in this particular reaction, ammonia, the base, is attacking water, the acid, and trying to strip its hydrogen. If successful, it's going to form this, which we call ammonium. They're trying to draw a tetrahedral shape, and hydroxide. Is this a favorable reaction? Well, when we look at these acid-base reactions, we want to go from stronger to weaker. So here's our base, ammonia. Going backwards, hydroxide's our base. So which one's a better base, hydroxide or ammonia? Hydroxide. So it's going from weaker to stronger, which means there's no driving force. But the extent of the driving force depends on how steep this energy transition is. If it's very steep, then we say no reaction. But if it's not so steep, there could be a little bit of reaction. There's some energetic molecule going up here. And so there could be a little bit. And so this is why there's this. It's called equilibrium. It's showing some forward and some reverse reaction. And indeed, some reaction does occur. It's not totally no reaction. That amount of reaction is minimal, though. It's only about 1% reaction in this particular case. But this is the reason why ammonia and water can participate in metathesis reactions. Ammonia and water, these aren't ions, but they can react to form ions. The ammonium ion doesn't participate in metathesis because all ammonium salts are soluble. The hydroxide does. There are lots of insoluble hydroxides. And so because of the formation of small amounts of ammonium and hydroxide, ammonia and water can participate in metathesis indirectly by the products here. That reaction is called hydrolysis, breaking apart water. So this is, some more vocabulary. Amphoteric. We talked about that before. What was amphoteric? What's the meaning of that? Yeah, it can react as an acid in one case, and in another it could react as a base. So it could go either way. Then we have forward and reverse reaction. Forward and reverse reaction just refers to this. If the energetics look like this is way more stable, then it's just downhill. This is a one-way reaction. This is only forward. If the energetics looks like this, then there's no reaction. But if it's somewhere in between here, there's a little bit of reaction. And so we have both forward and reverse when we have a little bit of reaction occur. So it depends on which way the ball rolls. All right, so this is the Bronsted. Then we go to Lewis. Lewis is the broadest, most comprehensive definition of what an acid and base is. And so we could actually we could actually not bother with Arrhenius, not bother with Bronsted, and just consider Lewis. We wouldn't miss any acids and bases. But that's not commonly done. We get rid of Arrhenius, so we'll never use Arrhenius really. But we'll retain Bronsted. The reason we're going to retain Bronsted is it's easier to subcategorize some acid-base reactions as Bronsted type. Because if we look at everything based on Lewis, it's a bit more tricky. Because Lewis bases are electron pair donors, Lewis acids are electron pair acceptors. So this is Lewis acid, BF3. Because it can accept this electron pair here in this orbital. This is a lone pair. You create a bond here. So this is an example of a Lewis acid-base reaction. For Lewis acid-base reactions, we need a Lewis structure. For Bronsted, we don't. For Bronsted, we just transfer an H. And so it's a lot easier. But for Lewis, things become more complex. So let me give you another example of a Lewis acid-base reaction. CO2. CO2 gas is known as a Lewis acid. And water can go either way. It's both a Lewis acid and a Lewis base. So it's an acid and a base. In this case, it's going to react as the base. For Lewis acid-base reactions, we need the Lewis structure. So we draw out the Lewis structure for CO2. It looks like this. We draw out the structure for water. And so how do they react? Well, the way they react is the Lewis base donates a lone pair. And so what we can have is, it's going to donate a lone pair to what? The oxygen or the carbon. Well, what we do first is we first look at the charges. Which one's more electronegative, carbon or oxygen? And so that gets the delta minus. Carbon gets the delta plus, this oxygen gets the delta minus. And so we can see that the carbon is going to be slightly positive because of the polarization of the electron file. And the same thing with water. Oxygen is more electronegative, so that's delta minus. The hydrogen is a delta plus, And so it's just minus and positive attractions. This delta minus on oxygen is going to be attracted to this delta plus on carbon. This is one possibility. We'll call it scenario 1. The other possibility is this delta minus on this oxygen is attracted to this delta plus on this hydrogen. That's scenario 2. So there's 2 possible Lewis acid-base type collisions. One in which this oxygen's lone pair gets donated to this carbon, the other in which this oxygen's lone pair gets donated to H. It turns out that number 2 is a dead end. It's a dead end by doing some trial and error. I didn't know it was going to dead end, but when we try to make something happen, we can't make anything happen. And so we're just going to go with 1. 1 will actually get us somewhere. And So following through with one, we got a situation like this, where the water now is going to donate a lone pair. The oxygen in the water is going to donate a lone pair here to form a bond. But if the oxygen forms a bond to that carbon, how many bonds are there going to be on carbon? 5. There's already 4 bonds there, 2 doubles. And now we're going to have 2 doubles and a single. That's 5 bonds. Carbon doesn't want 5 bonds. And so something has to give. And so what happens is these electrons get knocked out. And so we'll form a bond here and knock these out, so we'll end up with a net 3 bonds, or net 4 bonds, sorry. So what does that look like? Well, it's going to look like this. Does that look good? Yeah, some people will say that looks pretty good. Everything has an octet. I think we're good. Are we good? Weird lighting, sorry. Probably hard to see. Let me rewrite it over here. I'm going to rewrite that structure over here. Does that structure look good to you? Everything has an octet, but does it look good? No. What's wrong with it? Yeah, the formal charge is if we look at the formal charges, this oxygen has a positive, this oxygen has a negative. So one oxygen loses, the other oxygen gains. Does that sound good? No, it's going to be unstable. Unstable. It's going to be fairly reactive. What's the normal electronegativity of oxygen? You know? Around 3.5. But if you put a positive charge on oxygen, do you know what's going to happen to its electronegativity? Is it going to go up or down? Like a positively charged. Is it going to want the electrons more or less? More. And so this is going to have an even higher electronegativity, which means that these hydrogens are going to be more acidic. The reason they're going to be more acidic is because this oxygen now is going to pull the electron cloud even closer to it, making this hydrogen more positive. The more positive this hydrogen is, the more acidic we say it is. So this one's quite acidic. And this oxygen is going to be even more basic, because what makes a good electron pair donor? What makes a good electron pair donor is having negative charge up there, or more negative charge. And so what's going to happen is this molecule is going to vibrate like this. During the process of vibration, this lone pair gets pushed into this hydrogen and plucks it. What are bases? Bases are hydrogen ion. What did it say? Hydrogen ion. What's that word? Bronsted. This is not Lewis. Bronsted bases are hydrogen ion acceptors, but they had another word for it. Hydrogen ion removers. And so, in other words, this is going to remove this hydrogen as an ion here and leave these electrons here. If that happens, we end up with this structure. Do you recognize this structure here? Well, one, how does this one look compared to this? If you compare the right structure with the left structure, this one looks a lot better because everything has an octet and there are 0 formal charges. In fact, this looks pretty good, but unfortunately this isn't so good because this is also called H2CO3. H2CO3 is known as carbonic acid. Is carbonic acid stable? No, so it turns out that the reverse is favorable. Not the forward, the reverse is more favorable. And so CO2 in water is more stable than carbonic acid. But that's not to say that a little bit of carbonic acid can't form. A little bit of carbonic acid does indeed form. Right? And so we'll have a little bit. And so this is an example of a Lewis acid-base reaction here. Now, was it... Well, obviously, the Lewis acid-base reaction is more work than Bronsted. Bronsted is a lot easier, and so this is why I didn't really talk about these until later. So this is an example, another example of Lewis acid-base. So just to summarize here, arhenium is H plus and OH minus. We have Bronsted, which is proton source, proton remover. And then Lewis, electron pair acceptor, electron pair donor. We're going to use the last two. Let's take a look at Bronsted acid-base reactions again. This is acetic acid in water. Acetic acid is going to act as the acid, water is going to act as the base. So bases are proton removers, so this water will pluck off that hydrogen, the acidic hydrogen. That's what happens. When that happens, we form hydronium, and we're left over with acetate. How easy is it to remove a proton? Well, it depends on the structure. Some of these, it's super easy to remove a proton, like all of these. All of these are super easy to remove the proton because these are all strong acids. In fact, they're so easy to remove the proton that water can easily remove the proton. Is water a powerful base? No, water is what we'd call an extremely weak base. And so if water has no problem pulling the proton off those acids there, and then those acids must be strong. And they are. Those are the strong acids. And so when we look at HI is the easiest to remove the proton off of. Water comes along, takes the proton off, HI, forms hydronium, and we're left over with iodide. This is called the acid here, and its conjugate base is iodide. And there's a relationship between the acid and its conjugate base. If the acid is very strong, its conjugate base must be extremely weak. That is, will iodide come and pluck off the proton off hydronium? Hydronium should be easy to pluck the proton off, right? But is iodide strong enough to pluck the proton off hydronium? No. In fact, hydronium should be a lot easier to pluck a proton off hydronium than to pluck a proton off water. All right, this is the base, and its conjugate acid is this. And so these are conjugate pairs here. And the base is weak, water. That means its acid is strong, hydronium. So these are conjugates. We use conjugates to figure out driving force. When we look at the driving force for this, is there a driving force? And it turns out, yes, there is a driving force for this. The driving force is going from stronger acid to weaker acid, and stronger base to weaker base. So this is the driving force. So it turns out that strong acids do this. they react fully. This reaction here is called hydrolysis. So strong acids hydrolyze completely. There's good driving force for this. Well, this is a lot to write. And so we do this by shorthand like this. Hi goes to H plus iodine. This is what we call ionize. And so strong acids ionize completely. These two equations are the same thing. The reason they're the same thing is because H plus. H plus is very unstable. Does anybody remember what I said about H plus in the first week or two of school? Why it's so unstable? It's so unstable because of its high charge. Well, plus one's not high, but it's a high charge to size ratio because it's the size of a nucleus. And so H plus AQ doesn't exist. It'll react immediately with water. So this is just a shorthand way of writing this. A little bit easier. What about weak acids? Weak acids are harder to pluck the proton off. And the weaker the acid is, the harder it is to pluck the proton off. And so water struggles at plucking the proton off. The weaker and weaker it gets, the more difficulty water has to pluck that proton off. And so what happens with weak acids, let's pick a weak acid like acetic acid. Weak acids. Weak acids, water is going to have trouble removing the proton off. And so what we see is this. For weak acids, is there driving force for this? So here's the acid going in the forward direction. What's the acid going in the reverse direction? This is the acid base. This would be the acid base. Reverse. And so when we compare it, we're going from weaker to stronger. Weaker to stronger. So there should be no reaction at all, but it turns out, no, that's not entirely true. There's a tiny bit of reaction. That tiny bit of reaction means weak acids partially hydrolyze water. To show that, we do this. For strong acids, we just show it one way. For a strong acid, the ball's only going to roll downhill like this. But for weak acid, we have a lot of balls. Some balls have a lot of energy, some balls have not that much energy. But for weak acid, it's like this. It's uphill. So we should say no balls roll uphill, do they? But some of the balls have higher energy. And those higher energy balls might roll uphill a little bit, right? Temporarily. And come back down. And so this is what we mean by partially. And so it's about less than 1% can roll uphill. Less than 1% of the balls. And so this double-headed arrow, this is not a double-headed arrow. A double-headed arrow just has one, but this is an equilibrium arrow, call it. And so weak acids partially hydrolyze, or they partially ionize. Partially ionize. And a weak acid partially ionizing is going to look like this. HC2H3O2 acetic acid is going to partially ionize into H plus and acetate. It's mainly going to be this with a tiny bit of this. So it's like 99.9% this, 0.1% this. And so it's uphill, for sure it's uphill, but there's some high energy balls that might roll up. Because not all molecules have the exact same energy at room temperature. The weaker the acid gets, the harder it is to remove that proton. So let's take a look at the weakest acid here, hydroxide. How hard is it to take that proton off? Extremely hard. But if you do it, you're going to form H plus and oxide. Oxide is a powerful base. Oxide doesn't want to lose that proton. So it retains it. So Bronstet's a lot easier than Lewis because we have this is a chart of Bronsted acids. We have a method for figuring out the reactions, stronger to weaker. An interesting thing, though, does happen with the bases. The bases do not ionize. Bases only hydrolyze in water. Bases do not ionize in water. They only hydrolyze. You might go, hey, that's wrong. What about sodium hydroxide? Doesn't sodium hydroxide ionize? Yeah, sodium hydroxide ionizes. Sodium hydroxide ionizes into sodium ions and hydroxide ions. But we don't consider this the base. This we call the soluble salt. Soluble salts ionize. Like that. Soluble salts have strong electrolytes. They ionize. The hydroxide here is the base. So strong bases hydrolyze completely. That's a strong base. So strong bases hydrolyze completely. So let's give a couple examples. Example would be hydroxide. Hydroxide hydrolyzes completely. What does it form? When hydroxide reacts with water, there's a proton transfer. It's going to form water and hydroxide. Is there any change? No. There's no change, but there's change. What do you call that when there's no change, but there's change? When there's no change, you call it an equilibrium. When there's change, you call it dynamic. And so what do we call a no change scenario? Yeah, dynamic equilibrium. So this is a dynamic equilibrium. There's no change, but there is change. They're always colliding. You can't stop them from colliding. Oxide hydrolyzes completely. What does it form? Hydroxide and hydroxide. So oxide is going to hydroxide. So we're going from stronger base to weaker base. Stronger base to weaker base. And water, which is acid, is going to hydroxide. Well, what's that? This is going to be called stronger acid to weaker acid. So hydroxide is what we call amphoteric. It's amphoteric, but it doesn't go either way. It much prefers to be the base than the acid. Either way with equal ease. Weak bases partially hydrolyze. Weak bases partially hydrolyze. So the weak bases that partially hydrolyze, like ammonia. Ammonia and water. Ammonia is the base, it plucks the proton off to form ammonia and hydroxide. Yeah, this is going from a weaker base to a stronger base, and a weaker acid to a stronger acid. So there's no driving force, but it's not so severe. It turns out that about 99.9% this, about 0.1% that. And so just a tiny bit of hydrolysis. Well, that tiny bit of hydrolysis is enough to accomplish metathesis reactions. And so ammonia and water can participate in metathesis reactions because what happens is the Bronsted acid-base reaction occurs, generating hydroxide. And hydroxide loves lots of cations, so it can react. Weak bases do not ionize. If you have hydroxide or ammonia, let's take ammonia. What would ammonia ionize to? What would ammonia ionize to? Yeah, maybe it ionizes to nitride and 3 hydrogens. Does that look good? Break apart the ammonia into... No, it doesn't. All right, we'll stop here. We're out of time. So.